Okay, so hello and welcome back. So now in this video we're going to talk about the types of relations. So let me see what I did in the previous video. Okay, so in the previous video we did talk about some introduction about basically what we have here, and now we want to talk about types of relations. So let's see what these types of relations are. Types of relations. And basically so we know that basically a relation in a set, now there is something here that they have talked about here. Basically they use basically a, well, I don't really know what to call it, but they have used some way of talking about things. They call it a relation in a set A. They call it a relation. A relation. There is no. So the relation in a set A. Now I don't know exactly what they mean by this, because you could say that, for example, a relation. You could say a relation on a set A, which means that basically which would be a relation from A to A, right? But I mean, most probably, based on what I have read in the text, most probably they have used in and on interchangeably. So for now, what we can do, we will just take it as meaning the same thing, unless we come into some sort of contradiction or problem, and then we can, let me see. Let's take a look at the internet. Let's see what the internet says. Let's say that it is a relation in a set is a set, any set of ordered pairs which defines a relation between the first member of each pair and its corresponding second member. Now I think that's some sort of mistake that they have made. Anyway, that doesn't really matter. But it's some sort of consistent mistake, meaning that it's all over the text. Anyway, so basically we know that a relation in a set A, we know that the relation in a set A is a subset of basically the Cartesian product of A and A, right? So what that means is that basically if you have some set A, so suppose that you have some set, for example, like for example 1, 2 and 3. Now this set is basically something like this. So 1, 2 and 3, and that is your set A, and you have the set A over here, 1, 2 and 3, and then you have, if you want to calculate basically the Cartesian product of A and A, you would come up with all of these relations. I'm sorry, with all of these, meaning that you have to take basically one with basically the first element here, the second element here, and the third element here, and then you will take the second element with the first, the second, and the third element here, and then you will take the third element with the first, the second, and the third element here, and you will come up with this set as 1, 1, 1, 2, and 1, 3. Then you have 2, 1, you have 2, 2, and you have 2, 3. You have 3, 1, you have 3, 2, and you have 3, 3. Right, so this is the Cartesian product of A and A. Now, you can of course think of this as a relation, meaning that this whole set, basically you can think of this as a relation. Or you can take a subset of this set, for example, call it R, and say that, for example, R contains basically these elements, 1, 2, and 1, 3, these 3 elements. And you can call it R, and then that would be your relation. And basically that relation would be basically then would be shown this way, basically 1, 2, and 3. This is set A, and then you have the set A over here as this, and then 1 to 1, and 1 to 2, and then 1 to 3. So this would be the relation on the set A, characterized by some rule. For example, you can say that, for example, R is equal to basically this set of all the ordered pairs x, y, such that basically x and y, for example, belong to the set A, and for example x is equal to 1, for example, something like this, because over here x is always equal to 1, and you will get basically this set over here. So basically I can say that a relation, which is this thing over here, which is this set over here, is a set A. A relation in a set A is a subset of the set of the set basically denoted, characterized by the Cartesian product of A and A, right? And we have already talked about this extensively in relations and functions. We know what this is. Now, there is basically two things over here. We have basically the empty set. We have the empty set, and the set A, and the set Cartesian product of A and A. So you can call these two two extreme relations. And why basically TION. So why two extreme relations? You see over here, for example, suppose that you have some set A, which is the same thing as, for example, 1, 2, 3, and 4, right? And So consider a relation R. Consider a relation R on A given by, for example, R is equal to the order set the order pairs A comma B such that A minus B is equal to 10, right? Now, basically, if you this is a relation R on A, meaning that if I form the Cartesian product of A and A, I will get all of these elements as 1, 1 and 1, 2 and all the way up to 1, 4. Then I will have, for example, 2, 1 and 2, 2 and go all the way up to 2, 4. You have 3, 1, 3, 2 all the way up to 3, 4, and you have 4, 1, 4, 2 all the way up to 4, 4, and that would be basically the set A, the Cartesian product of A and A. Now here what I'm saying is that A is the ordered pairs A of the ordered pairs A and B, A comma B, such that A minus B is equal to 10. That means that the difference of A and B is 10. Which of course never is going to happen in as far as these ordered pairs are concerned, because the largest number that I have is 4 and the smallest number that I have is 1. Basically the biggest that the difference of these the biggest that the difference can make is at most 3. 4 minus 1 is equal to 3. If of course the difference is not a negative number, then at most it's positive 3. And we are saying that A minus B is equal to 10, which never happens. Which means that basically you can write R is equal to the empty set, right? Now, basically by the same logic, now if in the same situation, if I define another relation, for example R prime, and say that R prime is the set of all ordered pairs A comma B, such that basically the absolute value of A minus B, is greater than or equal to 0. Then of course all of these elements would belong to R prime, because as you can see, I'm saying that basically the absolute value of the difference of A and B is greater than or equal to 0. In case of all of these ordered pairs, the absolute value of the difference of A and B is greater than or equal to 0. Which means that R prime is actually equal to the Cartesian product of A and A, right? So and for the same reason, based on the reason that basically in the case of R prime, you're getting the whole set here, the whole set of the product of the Cartesian product of A and A, and in this case you are getting none of those basically ordered pairs. So then they have called this a two extreme relations, meaning that these two relations, you can say that they are located on the two extremes of the two extremes, meaning that on one extreme you're getting absolutely nothing, and the other extreme you are getting all the members all together, right? So now this basically, this takes us to, this leads us to the following definitions, right? And let's see what the definitions are. This leads us to the following definitions, and that is definition number 1. Definition number 1 is basically a relation R in a set A, a relation R in a set A is called empty relation, is called an empty relation, an empty relation, if no element of A is related to any element of A. If no element of A is related to any element of A, any element of A, that is R is equal to the null set, which is a subset of basically the Cartesian product of A and A, right? So that is called an empty relation. That is called an empty relation. And definition number 2 is basically a relation R in a set A, a relation R in a set A is called a universal relation, is called a universal relation if each element of A is related to every element of A. If each element of A is related to every element of A. That is, you can say that basically R is equal to the Cartesian product of A and A and A. Now both the empty relation, both of these, the empty relation and the universal relation, are sometimes called trivial relations. Are sometimes called trivial relations. Trivial relations. So that is basically that. Okay, so now let's do a couple of examples. So for example, example number 1 here is basically example number 1 is let A be the set of all the students of a boys' school. So let A be the set of all the students all the students of a boys' school. Okay. Now you want to show that the relation R in A, you want to show that the relation R in A given by basically R is equal to the ordered pairs A and B, such that A is sister of B, is the empty relation, and R prime, which is equal to basically the ordered pairs A and A comma B, such that the difference between heights of A and B heights of A and B is less than 3 meters, so this set basically is the universal relation. So basically, the way to solve this problem, you have the set A, which is the set of all the students, of a boys' school, right? So it's basically a boys' school. Now, you want to show that the relation R, which is given by this, is the empty set, and R prime is the universal set. So basically R is all the ordered pairs A and A comma B, such that A is the sister of B. So of course this relation R is going to be the empty set, because if you write A times, if you basically write down the Cartesian product of A and A, you're going to get basically A, you could think of A as, for example, this set, for example, student 1, student 2, student 3, and so on and so forth, all the way up to student n. So then A times A, or the Cartesian product of A, would be basically these ordered pairs as, for example, student 1, comma, for example, comma, student 1, for example. And then you would have student 1, comma, student 2. And then you would have all the way up to basically student 1, comma, student n. And you could go all the way up to basically student n, comma, student n. That would be the that would be basically the Cartesian product of A and A, right? And you can imagine that basically all of these students that you can see here, meaning that student 1 through student n, they are all boys, because this is a boys' school. And so it's just simply not possible that now we are taking this as A and we are taking this as B. So it's just not possible that A is a sister of B, because A in all of these cases is a boy. And so you can say that basically R is the empty relation. Is the empty relation. So that is about the basically R. Now about R prime, basically we have the ordered pairs A comma B such that the difference between heights of A and B is less than 3 meters. So the difference between heights of A and B is less than 3 meters. Well, it can, I mean, normally in a school, it can never happen that the heights between two students, basically heights of two students, or the difference of the heights of two students is more than 3 meters. That could never happen. And therefore this condition does include all of the ordered pairs A and B in the Cartesian product of the two sets. That means that you can say that basically R prime is actually the Cartesian product of the two sets A and B, which means that basically you can call R prime as the universal basically relation. As a universal relation. So that is about this example. That was example number 1. And as a remark, we said basically in class 11, we have seen 2 ways of representing a relation, namely the raster method, if I'm not mistaken. Now here there is some problem with this text. Sometimes you get some raster method of representing a set. A raster method is one way to show the elements of a set. That's actually raster, right? So here basically in the text it's been called the raster method, which is actually not right. It's a mistake. So namely we have seen 2 ways of representing a relation, namely the raster method and the set builder method. So we saw that, for example, in the case of we basically did have this in the previous videos. We had the raster method and the set builder method. And the set builder method. However, a relation R in the set basically 1, 2, 3, 4 defined by R is equal to this is also expressed as basically, there is basically one more notation here that you can use, and that is you can say that the relation R in the set basically 1, 2, 3 and 4 defined by defined by R is equal to basically all the order pairs A, comma B, such that B is equal to A plus 1, right, is also expressed as ARB if and only if and only if basically B is equal to A plus 1. So instead of writing basically R is equal to basically the set of all ordered pairs A, comma B such that B is equal to A plus 1, you write A and some space here and R and then some space and B if and only if B is equal to A plus 1. Some authors basically use this notation for basically this situation. And so we may actually use it in this text whenever it's convenient, which means that it's basically the same thing. So that means that basically R is a relation, which means that R is a relation in the set A. R is a relation in the set A, in this set over here, defined by this rule, which is R is equal to, for example, B is equal to A plus 1, and that is expressed by ARB if and only if B is equal to A plus 1. Okay. Now, if basically if A comma B belongs to R, if A comma B belongs to R, we say that A is related to B. We say that A is related to B. A is related to B, and as and we denote it as, and we denote it as A is related to B. So one of the most important relations which plays a significant role in mathematics is an equivalence relation. So that is called basically an equivalence relation. An equivalence relation. Now, to study the equivalence relation, we first consider three types of relations. So there are three types of relations that we need to learn first, and then through those three relations, we can basically learn the equivalence relation. And those three relations are called reflexive and symmetric and transitive. Reflexive, symmetric and transitive. Okay. So, what is reflexive, what is symmetric, and what is transitive? So as a definition number 3. Definition number 3, we have a relation R in a set A is called reflexive. A relation R in a set A is called number 1, reflexive if basically a comma the ordered pairs a comma a, if the ordered pair a comma a belongs to R for every a belonging to a, for every a belonging to the set A, meaning that for every a, so basically we are talking about the relation R in a set A. So we have the relation R and we have the set A, and this relation R in the set A is called reflexive if the ordered pair a comma a belongs to R, right, for every a belonging to the set A, meaning that for every a belonging to the set A, then basically this ordered pair belongs to the relation R, meaning that, for example, if the set A is, for example, something like if the set A is something like 1, 2, 3, and 4, so over here A is, for example, A is equal to 1, then in that case basically 1 comma 1 has to belong to R. And if, for example, A is equal to 2, then 2 comma 2 has to belong to R. And for A is equal to 3, then 3 comma 3 has to belong to R. And for A is equal to 4, then 4 comma 4 has to belong to R, and so on and so forth. And so on and so forth. For A is equal to n, basically n comma n has to belong to R. And if that is the case, then the relation R in the set A is called reflexive. Now, basically the second part is symmetric. So now we know what reflexive is. Now let's see what symmetric is. So basically you can say that the relation R in a set A is called symmetric. A relation R in a set A is called symmetric. Is called symmetric if A1 comma A2 belongs to R, belonging to R implies that basically A2 comma A1 belongs to R for all A1 and A2 belonging to R, belonging to A. For all A1 and A2 belonging to A, right? So what that means is that basically what we are saying here is that a relation R in a set A is called symmetric if basically A1 comma A2 belonging to R implies that basically A2 comma A1 belongs to R for all A1 and A2 belonging to R, which means that, for example, if 2 comma 3 belongs to R, then basically 3 comma 2 also belongs to R. Or for example, if 3 comma 5 belongs to R, then 5, 3 also belongs to R, and so on and so forth. And to say it basically in general, you can say that if A1, A2 belongs to R, that implies that A2, A1 belongs to R for all A1, A2 belonging to R, right? So that is called symmetric. Then basically that relation R is called symmetric. The third term that we have here is called transitive. Transitive means that basically if you can say that a relation R in a set A, a relation R in a set A is called transitive. If A1, A2 belonging to R, if A1, A2 belonging to R, and let me write it this way so you don't get. So if basically A1, A2 belonging to R and A2, A3 belonging to R, implies that if this basically implies that A1, A3, A1, A3 belongs to R for all A1, A2, A3 belonging to R. For all A1, A2, A3, for A1, A2, A3 belonging to R. Okay, so basically this was basically the definition of a reflexive relation, symmetric relation, and transitive relation, right? Now, basically what we were primarily talking about another type of relation which was called the equivalence relation, equivalence relation. Right, so we wanted to know what this was, and then we got into those three types of relations. So now definition number 4. Definition number 4 is a relation R in a set A, a relation R in a set A, is said to be an equivalence relation, relation if R is if R is reflexive, symmetric, and transitive. Symmetric and transitive. So if R is reflexive, symmetric, and transitive at the same time, then you can say that the relation R in set A is basically an equivalence relation. So now let's do a couple of examples. Example number 2 is, let T be the set of all triangles in a plane. I don't know what happened there. Okay, so let T be, this is example number 2. Let T be the set of all triangles in a plane with R a relation in T, with R a relation in T given by T, basically given by R is equal to all the ordered sets T1 and T1 comma T2 T1 comma T2 such that T1 is congruent to T2, such that T1 is congruent to T2. You want to show that R, show that R is an equivalence relation. Right? So basically T is the set of all triangles in a plane, and R is a relation in T given by basically R is equal to all the ordered all the ordered pairs T1 comma T2 such that T1 is congruent to T2, right? So T1 is congruent to T2, and you want to show that R is an equivalence relation. So to show that basically R is an equivalence relation, we need to show that R is reflexive, symmetric, and transitive. So basically we need to in order to show that in order to show that R is an equivalence relation, we need to show that R is reflexive, symmetric, and transitive. So which means that basically in order to show that R is in order to show that R is reflexive, we said that the definition for reflexive was that we said that a relation R in a set A is called reflexive if basically, so we said that basically reflexive was if A comma A belongs to R for every A belonging to R. For every A belonging to R, right? So what that means is that in this case where we are dealing with these triangles, we have to show that if T1, for example, belongs to A, for example, for any T1 belonging to for any T of I basically belonging to R, we have to show that T of I comma T of I belongs to R, right? So for that, so let me write this down. So in order to show this in the context of this problem, so basically your set T over here, you can imagine that your set T is basically a collection of all of these triangles, T1, T2, T3, all the way up to T of n, right? So I can denote all of these T's as every member of T can be generally referred to as T of I, right? We can refer to them as T of I. And so we need to show that basically for every, to show that R is reflexive, we need to show that for every T of I belonging to the set T, the ordered pair basically T of I comma T of I belongs to R, right? So how do we do that? So basically you can imagine that every triangle, basically T of I denotes any triangle. So you know that any triangle is congruent to itself, right? So you can say that since every triangle in the plane is congruent to itself, therefore for every T of I belonging to basically T, then basically T of I comma T of I belongs to R. And so R is basically reflexive, right? So let me see. That is basically the first part, right? Okay, so the next part of this question, we want to show that basically R, so over here we showed that R is reflexive. Now we need to show that R is also symmetric. So to show that R that R is symmetric, basically the condition for that is basically if we said that if the condition that we talked about about the symmetric, we said that if basically A1 comma A2 belongs to R, actually there is no if here. You have to say that basically you have to, the condition is A1 comma A2 belonging to R. This implies that basically A2 comma A1 also belongs to R, right? So that means that and of course for all A1 comma A2 belonging to R, right? So this is the condition. Now to show that R is symmetric, we use this condition, meaning that A1 comma A2, A2 comma A1. So here basically we are talking about this triangle, and we said that basically R here is basically T1 comma T2. T1 is congruent to T2, right? So what that means is that now if you can write T1 is congruent to basically the R over here is basically the definition of R is basically all the ordered pairs T1 comma T2, such that T1 is congruent to T2. Now since T1 is congruent to T2, then of course so basically you know that if T1 is congruent to, of course you know that we are talking about triangles, if T1 is congruent to T2, then T2 is also congruent to T1, right? Which means that if if T1 comma T2 belongs to R, then T2 comma T1 belongs to R as well for all T1 and T2 belonging to the set T, for example, right? Which proves that basically R is basically symmetric. right? Okay, so for the next part, you want to prove that, you want to show that R is also transitive. So in order to show that R is transitive, so basically what you need to do is basically, we said that the condition that we use for a relation to be transitive, the condition that we use, we said that if A1 comma A2 and belongs to R, and A2 comma A3 belongs to R, this implies that A1 comma A3 belongs to R for all A1, A2 and A3 belonging to A. Basically, that was the condition that we used. Now, here you could argue that basically in the case of these triangles, we said that basically R is T1 comma T2. R is basically the set of all such ordered pairs T1 comma T2, such that T1 is congruent to T2, right? So what that means is that if basically if we have T1 and T1 comma T2, we have T1 comma T2 and let's say T2, for example, comma T3, if these two belong to R, that implies that T1 comma T3 belongs to R, because T1 is congruent to T2 and then T2 is congruent to T3. That means that T1 is congruent to T3. That then you can say that T1 and T1 comma T3 belongs to R. Therefore, which shows that basically R is transitive. R is transitive. Now we have shown that R is basically reflexive. R is reflexive and symmetric and transitive. And therefore R is basically called an equivalence relation. Is an equivalence relation. So what that basically means is that first of all, basically what that basically means is that the equivalence relation, meaning that the relation first of all is reflexive, meaning that basically for every A belonging to the set A, then A comma A belongs to R. And symmetric means that basically if A1 comma A2 belongs to R, then A2 comma A1 also belongs to R for all A1 A2 belonging to R. And transitive is basically this thing over here, which is A1, A2 belonging to R, and A2, A3 belonging to R. If that's the case, then A1, A3 also belongs to R. And that sort of relation where all of those three things are the case, then we call it an equivalence relation. So I think that is it for this video. We have a couple more things here to cover. So I'll end this video here, and then we will continue the same discussion in the next video. I'll see you in the next video.